All right, so this is video. It's just going to go over the hard drive practice problems. Again, you shouldn't just be starting with this video. Hopefully you've tried it already, and you can use this to sort of check your answers. And then if you're not getting the right answer for one of them, listen to my explanation. If you are getting the right answers, there's no need to watch this whole video. You can just skip around to see the answers and check to see if there's any that you need reinforcement on. All right, so it says, suppose your hard drive has 512 tracks per surface, 256 sectors per track, a rotational speed of 17,500 RPMs, and it takes 0.004 milliseconds to move the read arm one track. If each sector contains 1,024 bytes and the disk has 4 double-sided platters, answer the following questions. So, Part A, exactly how many bytes can be stored on the hard drive? All right, so we're going to pretty much need to use just about all of these numbers in the descriptions here to answer this question. So first it says that we have 4 double-sided platters. So if we have 4 double-sided platters, that means we have 8 surfaces. All right, each of those surfaces has 512 tracks. And remember, the tracks are like the rings. So right there, those are your tracks. And then each track has 256 sectors. And the sectors are the lines that kind of make the wedges. All right, so the combination of tracks and sectors divides us up into these little blocks of information. So those vertical lines right there mark our sectors. So we have 8 surfaces. Each of them has 512 tracks that are divided up into 256 sectors. All right, so this is our tracks. This is our sectors. This right here is giving us the total number of blocks. And we're told that each block has 1,024 bytes inside of it. All right, so this is going to give us, these 3 right here is going to give us the total number of blocks. Each block has 1,024 bytes. So all we'd have to do at this point is multiply those out, and we end up with 1,073,741,824 bytes. All right, so that's 1,073,741,824 bytes. And again, I got to that just by multiplying these 4 numbers together. 8 surfaces coming from the 4 double-sided platters, 512 tracks. Each track is broken up into 256 sectors. So this gives us the total number of blocks. Each block has 1,024 bytes, so that's our total number of bytes. So for your answer to A above, exactly how many gigabytes of storage is this? So a couple of ways you can do this. You can either remember that a gigabyte is 2 to the 30th. So you would divide this number right here by 2 to the 30th. 1,073,741,824 divided by 2 to the 30th power. Or if you don't remember that that's 2 to the 30th, we can go through and do it step by step by step. So we could go 173,741,824. And we could say to ourselves, all right, well, 1 kilobyte is 1,024 bytes. And then we can be like, okay, well, 1 megabyte is 1,024 kilobytes. And then we can be like, oh, okay, 1 gigabyte is 1,024 megabytes. All right. Either way, these are going to give you the same answer, because effectively what we're doing here is we're doing 1024 times 1024 times 1024, which gives you the same exact thing as 2 to the 30th. So two different ways of thinking about it. One is not more correct than the other. This one just requires you to remember that a gigabyte is 2 to the 30th. This one just works on that 1024 principle, where 1024 kilobytes is a megabyte, 1024 megabytes is a gigabyte, and so on and so forth. Either way, they're going to give you the same exact answer, which is 1. All right, so it's exactly 1 gigabyte when you work that out. All right. So again, doesn't matter which way you do it. Both are giving you the same exact answer. Whichever way you remember is fine by me. All right, suppose the arm needs to move 100 tracks towards the center. How long will that take in milliseconds? All right, so this is pretty simple. It tells you that it takes 0.04 milliseconds to move each track. So this is just going to be 100 times 0.004 milliseconds. We're multiplying it by 100. So that means that decimal place moves 2 spots to the right, and we end up with 0.4 milliseconds. Okay? So don't make that one any harder than it has to be. All right. How many milliseconds does it take to do a complete revolution of the platters? All right. So we know that it can do 17,500 revolutions in a single minute. We want to find how long it takes to just do one revolution. All right. So let's take a look at this. All right. So it takes 1 minute to rotate 17,500 times. So 1 minute for 17,500 rotations. All right. We want this in milliseconds. So we can say to ourselves, okay, well, 1 minute has 60 seconds. And 1 second has 1,000 milliseconds. All right. So if we multiply across there, we know that in 60,000 milliseconds, we can do 17,500 rotations. And then if we divide those two numbers, so 60,000 divided by 17,500, we're going to see that it takes 3.43, we'll round it here. So 3.43 milliseconds for one rotation. All right, so again, 17,500 rotations per minute, which means that a single rotation is going to take us 3.43 milliseconds. All right, how long does it take to read in the contents of a sector, assuming that the arm is already over the proper tract and the start of the sector is already under the arm's read-write head? So that means our seek and our latency is 0, and we're only worried about the transfer time. So the transfer time is basically the length of time it takes to make a rotation divided by the number of sectors that exist. So in our case, it takes 3.43 milliseconds for a single rotation. And on this hard drive, the track is broken up into 256 sectors. So the time to do just one sector is going to be the 343 divided by the 256. 3.43 divided by 256. We'll go to round this to 0.013 milliseconds this time. All right, so that's the amount of time it would take to read a single sector. All right, and you can divide by 256. I think in the notes I showed it as multiplying by 1 over 256. I mean, obviously, mathematically, those are the same thing. So don't let this trip you up in any way, but they're going to give you that same answer. All right. If the drive's rotation speed changed from 17,500 rotations per minute to 7,200 rotations per minute for each aspect of the drive's access time below, state whether it will change and then whether it will get faster or slower. If it will stay the same, just write same in the blank. All right, so basically this is, do you understand what each of these terms mean? All right, so the seek time is the time for the read-write head to move to the proper track. All right, so it has to move in and out to get to the right track. That has nothing to do with how fast the disk is spinning. All right, the arm is independent of the spinning, so this one would stay the same. Even if the disk is spinning slower, it's not going to affect the speed at which the arm moves in and out. Now, latency is the time for the disk to spin to get into the proper position so that it can read the necessary data. So the disk has to spin to get to the starting point of the data. And we call that the latency time. Since that deals with the disk spinning, that is going to be affected. And since we're doing less rotations per minute, this is going to get slower. And then last but not least, the transfer time is the time it takes to actually read in the data. And again, we read in the data as the disk rotates. So since that relies on the disk rotating, this is also going to be slower since we're doing less rotations per minute. And then the last part here is filling in one of these charts. All right, you're going to see a lot of these charts. There's one on here, there's one on your homework, there's going to be one on your eventual test. So get used to these. All right, so fill in the following chart based on 17,500 rotations per minute, which was the original number from the problem. All answers should be in milliseconds. So in the best case scenario, the read-write head will already be on the proper track. So your seek time will be 0 milliseconds. You won't have to spend any time moving that read-write head. In the best case scenario, the disk is already in the proper position, so you don't have to worry about spinning it. As such, the latency will also be 0 milliseconds. Now, the transfer time is the time to actually read in the data, and we actually already calculated that on the front here. All right, we calculated the time it takes to read in a sector. This is the transfer time. We used it based on that 17,500, so this is the answer for that block right there. It's the same 0.013 milliseconds that we got from the previous page. So when we're talking about the total time, we just add those together and we get 0.013 milliseconds. All right, now worst case scenario, right? The problem told us that there were 512 tracks. So the absolute worst case is that you're on the innermost track and have to go to the outermost track, or vice versa. You're on the outermost and you have to go to the innermost. So that means you're going to be moving a total of 511 tracks, right? Because if you're going from the innermost to the outermost, yes, there's 512 different tracks, but you're only moving 511 times to get to that track. So it's going to be 512 minus 1, or just 511, times the amount of time it takes to move a track, which the problem tells us it takes 4.004 milliseconds to move one track. So we're going to multiply this by 0.004. And that's going to give us the worst case scenario time. So 511 times 0.004, we end up with 2.044. This is 2.044 milliseconds. Latency is, again, the time for the disk to spin into the proper position. In the worst case scenario, you're going to have to do a full rotation because the disk is just slightly past where you need to go. So we've already calculated the amount of time for a full rotation. All right, we saw that here in question or part D. It's 3.43 milliseconds for one rotation. So we're going to write 3.43 milliseconds here for one rotation. And then the nice part is the transfer time never changes, right, as long as the rotations stay the same. So we're still using this 0.013 milliseconds. And then we can just add those together. So we've got the 2.044 plus the 3.43 plus the 0.013. And we end up with 5.487 milliseconds. Now, usually I get asked, like, what do you want me to round it to? My general rule is I don't get that worried about rounding as long as you're rounding correctly. So if you had dropped the 4 here and just said 2.04, I would have been fine with that. If you had rounded this up to 2.05, that would have been a problem. Also, you kind of have to think about the problem that you're doing and don't round to something that doesn't make sense. I mean, when we're dealing with these small milliseconds here, don't just round this to 2, 3, and 0. All right, that would be like a poor rounding choice. But in this case, you know, to the thousandth place, to the hundredth place, you know, somewhere in that neighborhood is fine. All right, last but not least is the average case scenario. All right, so from our notes, we learned that on average, the arm is going to have to move over 1/3 of the tracks. So we've got 1/3 times 512, because on average it's going to move over 1/3 of the tracks, times the 0.004. All right, so this right here is the key for the average, and that's just a number that you need to remember when you're doing these problems. But at that point, it's just putting into your calculator 1/3 times 512 times 0.004, and you're going to get, let's go, 0.683 milliseconds. All right. Now, when it comes to latency and you're talking about spinning it to the proper place, on average, it's going to take half a rotation. So if a full rotation is 3.43, we want to know what half a rotation is. So we're just going to do 1/2 times 3.43. Oops. So 0.343 times 0.5, and we get 0.1715. So I'll just round that to 0.172 milliseconds. And then again, the transfer time stays the same. So that's 0.013 milliseconds. Right? So that part is consistent across all three. And then we would just add those together. So we've got our 0.683 plus our 0.172 plus our 0.013. And that's giving us, wait a second. I apologize. When I typed this into the calculator, I typed in 0.343 instead of 3.43. So that's why that answer doesn't make any sense. So 3.43 times 0.5 is 1.715. So I apologize for that. Let's just write 1.715 milliseconds. Again, my bad. Sorry about that. And then when we add these three together, plus 0.013 plus 0.683, we get 2.411 milliseconds. All right. So again, that's how you would work through one of these charts. these should be your final answers. Again, if you've got something slightly different because of rounding, not really worried about that, as long as you're rounding correctly. All right, so I hope this was useful. If you have any questions, let me know. All right, bye. Actually, here, let me show you all the answers, and then you can skip to the end and check the answers. And then if you're good, you don't have to watch the whole video. So here's this answer for A. There's B's answer. That's just showing the different ways you can calculate it. There's C. There's D. There's E. Same, slower, slower. 0, 0, 0.013 for a total of 0.013. 2.044, 3.43, 0.013, 5.487, 0.683, 1.1715, 0.013, 2.411. All right, that's it. Have a great day.